So to get us kind of over this hump of being a little straggling, I had an idea. We're going to try it once. We're going to try it once as a group here, okay? We're going to kind of play with the room next to us a bit and see if we can kind of get them questioning some things and wondering what's going on in here. It's football season, right? How many football fans we got in the room? Come on, hands in the air.
2.
Really? Okay, well the rest of you pretend that you're football fans, okay? So what we're going to do kind of throughout, and Kevin has no idea, this is like, I'm just going rogue.
I just woke up 30 minutes ago, so.
So we want to wake Kevin up. Okay, what we're going to do is, at some point we're going to say, hey, we just scored a touchdown, and I want you all to clap and hoot and holler like we just scored a touchdown, like our team, like your favorite team just scored a touchdown, won the Super Bowl, I don't care, whatever you want to think about, the World Cup, sure. So when we say we scored a touchdown, I want you all to just give it your all, okay? And we're going to try it once. If you guys fail, we'll just abort, all right? Okay. See, we're 2 minutes short still, so we have this rehearsal time. Okay, you guys ready? You ready to try it, right? Okay, all right. And we scored a touchdown! That's not bad. I think you guys can do better next time, but that's okay. Let's roll with it. You got a clicker for me?
There's a clicker.
All right. So we are talking about framework for CAV modeling in mixed traffic with Vissim. So basically what we're talking about is, in here, Lucas and others figured out how to do what we're doing now, and they're going to basically give it to you all. So that's cool. Thanks, Lucas. But we're going to share what we did and how we did it. And I honestly think, I told Lucas, I said, I don't want you to come today. I want your feedback, because I think that there's a lot of things that we can learn from what you're doing. I think there's probably still some advances that maybe we can discuss within PTV software. So I think this is going to be great. So we actually did this for a project, for a client, talk a little bit about the project, kind of walk through kind of the background of it a bit, and then we'll get into the details of it. We had to go through some operational behavior assumptions, Vissim model setup adjustments, scripting, and then just a little bit into some of the results that we're getting. So the project, this was for Colorado DOT. They wanted to have something that they could set up, a framework, that they could apply to any Vissim model. So say that they had a Pell project, and they said, we've got this calibrated model, now we want to see some scenarios where we've introduced CAVs into it. We want something that we can just take a step-by-step process with some scripts that are already done, and just say, consultant XYZ, here's the process, here's the scripts, add it to your model that you've already done, and test its adoption rate. Something that was an easy plug and play. And so basically it was a step-by-step document, was scripts, some sample model files, and with that, in theory, anyone could pick it up and apply it. For this, they wanted us to look at developing the framework for various facility types. So they wanted to make sure that whatever this framework was, it would work for a lot of the different facilities that the DOT has in their jurisdiction. So they have a lot of divided rural facilities, like many states do, or all states do. They've got some pretty congested conditions in urban environments, namely around Denver. They've got undivided highways where they've got passing in the opposing lane. They've got mountain passes with tight curves. So they wanted to make sure that whatever we develop was applicable to all these different types of facilities. So it presented some unique challenges for us. You kind of see some of the different, so the facilities that we selected were just example ones within each of these. They all had different characteristics. The divided rural was a bit longer. It was a 4-lane roadway, 80 Ts in the mid-20s, 18-20% trucks. The divided urban, much bigger facility, much more traffic, pushing 300,000 ADT in some segments. Undivided state highway, low amount of traffic, high trucks passing the opposing lanes, mountain pass, limited access, 2 lanes in one direction, 1 lane in the other to allow for passing over trucks that are trying to climb. So some unique conditions. Okay, now you ready? Ready? We're gonna do it again. Okay? Hey, we just scored a touchdown! Kevin, you're not bringing it yet.
Yeah, no, that's it's way above my head.
All right, CAV operational behavior assumptions. So before we got into Vissim, and figured out what things we want to update in Vissim and how do we want the scripting to work. We had to start thinking about what do we think the CAVs will operate like. We need to think about that first, right? We need to think about what do we want to try and model. And we had done this on another project before already, and we kind of erred on the side of caution a bit. We kept the assumptions pretty conservative. We didn't want to get too carried away thinking that CAVs are going to just completely change everything. We're going to have 2-inch headways going, hair on fire down the freeway. I mean, we're going to have vehicles merging and absolutely no space, in front of them or behind them once they get in the lane next to them. We weren't trying to get that crazy. The fleet composition, we kept the same as all of our non-CAVs. We didn't say we're going to have a one-size-fits-all vehicle for cars, a one-size-fits-all vehicle for trucks, and roll with it. We're going to assume that if there's trucks, we've got single-unit trucks, we've got heavy vehicles that are various sizes. We'd still have that variation in size for automated trucks. That was the assumption. Maybe it'll happen that way, maybe it won't. Speeds. Posted speed limit was what we started with. We wanted to form platoons within the network, so we didn't want the speeds to all be the same because then vehicles would never join one another unless they were forced to slow down. So we said, okay, posted speed, that's for max speed. Min speed, 5 miles per hour or less, arbitrary. But it gave us an opportunity to get vehicles to come together. Car following, we did increase the look ahead and look back distance. I don't know that it really changes much within the network, but we just tried to say, well, we're going to have more spatial awareness. Sure. Reduce stochastic car following. Yeah, we're not going to have this ebb and flow, the imperfection of the human driver, and that's what PTV is doing a lot with their out-of-the-box AV driving behaviors now. Is kind of tinkering a lot with those car following behaviors. Reduce time gap. So that's more on the uninterrupted flow side, which is really what we're focused on here, which is more the uninterrupted flow, not the arterials, uninterrupted flow. So freeways, highways, etc. So we're looking at that reduced time between CAVs, where we are forming these platoons. For uninterrupted flow, we did have some locations within the model that were uninterrupted flow, were interrupted flow, and for those we just said we're going to have some increase in saturation flow, just so that our queuing maybe back towards the freeway was a little bit less. Let's decrease our spacing between vehicles on our links that have Freedom to 74 applied to them. Basically, let's make it a 25% increase in sat flow. So that was kind of where we got there. CAV lane changing, we really didn't change much of the lane changing from what was in the driving behaviors for the non-CAVs. We left that pretty much the same. I think there's a lot of opportunity there to look into that and do a lot of research. We don't know a lot yet, and given that we didn't know a lot, we didn't want to start making changes and be too adventurous. Platoon sizes, we're going to do this a bit. The platoon size that we've got is actually something that's user-defined in our framework. These were the values that we use for these corridors. We use 5 cars and 3 trucks in the divided row and 3 cars and 2 trucks for everything else. Basically, we want to make sure that non-CAVs in mixed traffic have the opportunity to make lane changes when they can. If we've got a platoon of 10 trucks, I've got a non-CAV next to it, I've got all of a sudden this 300-foot long platoon, and how do I get in the lane next to me when I got to exit? I don't know. Platoon formation, much like a lot of others, and I know what PTV is doing, it's all generating platoons within the same lane. We're not looking cross lane, we're not trying to merge vehicles together, and actually, the more I thought about it was, potentially if we try to do that, we're actually going to increase the turbulence in the network when we do that. If we start saying we're going to make all these extra lane changes to form platoons, we could, in theory, be making some additional turbulence in the network. I don't know, maybe there's some opportunity there, but given that we don't know it, we didn't incorporate anything like that. speed adjustments, we'll get into that. Platoon continuity, that was a big thing. We really wanted the platoons to stay together unless a vehicle was wanting to leave for a downstream turn decision. So if a lead vehicle was slowed down, we didn't want a trailing CAV to say, oh, I'm going to get out of the platoon. We wanted them to operate as a unit and only exit the platoon if they had a downstream turn decision. So Vissim model adjustments. I guess the way we approached it was, okay, now we kind of understand what we want to model. What do we need to do in Vissim to do what we've just kind of walked through as our assumptions? And then thinking about, along the way, how the scripts are going to be developed, and then it was kind of an iterative process actually. You know, we go through this, set this up, develop the script, figure out, oh, we need to make some changes in the script, and in Vissim we kind of go back and forth. So it was adding vehicle types, CAV, lead vehicles, platoon vehicles, the classes, speed distribution we talked about, basically a 50 mile per hour speed distribution for CAVs. It was just for CAVs, so 45 to 50 miles per hour. That was our range, that's what we looked at. We updated the driving behaviors. We started with, I actually had some conversations with PTV folks. We started with the out-of-the-box AV driving behaviors. The normal and the all-knowing were kind of the two that we were looking at. Had some conversations with folks, where do some of these values come from? And we adjusted them some. So basically a lead CAV was, or a CAV that was traveling by itself, was looking at the AV normal behavior for the most part. We made a few tweaks to the driving behavior a bit. Where they're following, the time gap on that was 9/10 of a second. It's kind of like the default out-of-the-box value. The CAVs that were following a platoon, we wanted about a half-second time gap between vehicles. The all-knowing one, I think, is a 6/10 of a second is the CC1 value. And we ended up going with 0.45. Just tried a lot of different testing. We tried a lot of different with the platoons and that. Watched a lot, tracked vehicles. That got us about half a second between vehicles. So that's what we went with. Vehicle compositions, just to get the adoption rate in there. Sometimes, so now we're actually working with applying the framework on a project, and the inputs and routing gets a little interesting. We've got some managed lanes now, where we are looking at just CAVs in the managed lane. And for that, we're actually duplicating our routing, and we're adjusting routes specifically for CAVs from non-CAVs. So again, it's part of the process. So I told Kevin, so this is the script development section. This is my scripting guy. So when there's all this computer stuff that's all over my head, I just call this guy up and I say, hey, this is what I want to do. You can figure it out, I'm sure. So Kevin gets the cool stuff. I'm probably going to interject at some point in time, because it's the cool stuff, but
Yeah,
I'll let you take it.
Yeah, I'm not really sure why Mike thinks this is the cool stuff.
It's the cool stuff.
I think everything I do is pretty boring. Yeah, so Mike is right on that. He would basically call me up and say, hey, the script is broken, or the script is doing this, we needed to do something else. So we would get on the phone for at least 2 hours. I would take a little nap on the floor underneath my desk, and then towards the end of the phone call, I would finally get back up and get ready to hang up the phone. Mike knew about 10 minutes into our phone call that I was falling asleep and wasn't paying attention, and so I'd make him repeat what he said about 30 different times during that phone call. So the way that we got all of this platooning logic implemented within the Vissim context is we used Python tied into the COM interface. And 99% of the script basically just goes through every single vehicle, determines whether or not it can be platooned, and then if it can, we put a bunch of logic in place that determines what speeds the vehicles should be traveling to catch up to their leader vehicle. And so that's 90% of that is gap closure, 10% of it's just checking to see whether or not these cars can be platooned or not. And the last 0.001% is basically setting the desired speeds of all of those vehicles and a couple other attributes that we needed to track during the course of the simulation. We set up the script to run every 30 seconds within the context of, 30 seconds, no, half second. It's half second. To go through and look at every single car in the network, determine which cars were added since the last time set, which cars were taken away, and that way we could start to trim down which cars we needed to process. Let's see, I guess I'll go through these little bullet points here. One of the first things that we do is check to see whether or not that vehicle is on a Wiedemann 99 facility, and if it is, then it's platoonable. If it's not, sorry, you're out. We take a look and see what distance that vehicle is from the vehicle in front of it, if that object type is a vehicle. And if it's within our threshold, then we begin the joining process. That's the next part, join the CAV. So we adjust the desired speed decision based off of the leader vehicle in front and slowly watch it merge up with the vehicles ahead. We did a lot of other It's kind of interesting stuff, but I'm not going to get into those boring details. Mike loves those details. And then we also had situations where CAV vehicles want to get out of the platoon, so we had to go through some additional logic to merge platoons if they got broken up, or if a vehicle left it, we had to go back and apply the same logic. So I was asked by Mike, because we were both lazy, I'm lazier than him, to write a script that adds in all of those user-defined attributes for the vehicle so that we could track it.
Yeah, I am lazy about that.
Yeah, he didn't want to do it. He didn't want me to write. He surely didn't want me to write how to do it.
It's like a 5-minute exercise, but that's 5 minutes, that's it.
Yeah. So you have a script that goes through, adds all the user-defined attributes. Those are the things that we need to track for each vehicle. And then we also have, that script also adds the additional event scripts that we needed during the simulation. So we have an initialization script. We have a script that's called every half second. That's basically the bulk of the work. And then the last script is just sort of a, finalize, save some data, write some logs, and move forward. On the left side here, don't know how easy that is to read. I am blind, but I can see it. That's just basically an ini file that Mike could sit there and play with certain parameters to adjust how vehicles were joining the platoon. One of the, I think, more innovative things that we thought of eventually is the function that we use to define what the gap closure speed should be of the vehicles in front of it. So for a while there, we used a linear thing. That didn't work out so well. So we ended up moving it to like a logarithmic function. So the further away the vehicle is from the vehicle in front of it, they would have higher speeds, but once it started to get closer, we would minimize that speed. And because we were seeing a lot of issues with vehicles changing lanes and then taking away all of that lovely platoon logic that we had in place. And that brings us up to this. This is the one that I think Mike really wanted this. Mike really wanted this slide.
Yeah, I'm getting excited. I'm getting excited again. I think our team just scored a touchdown. Yeah! The folks walked in late. They have no idea what we're doing.
And I was here, and I still have no idea what we're doing. All right, so I'm going to get this started a little bit, and then Mike is definitely going to take over this because he's just way too excited.
Get a little. Yeah.
So one of the first things, and this is just a total like software bug on my behalf from the code. We were running into issues where we had trailing vehicles, 5 vehicles back, that had a desired speed decision of like 98, 105 miles. That was because I was setting it that way. We were doing just like a flat percentage increase of vehicle speeds from the vehicle in front of it. So we were doing 5% times 5% times 5%. So eventually we were.
You guys have big speeds.
Yeah, that's what it is. We also came into some issues where, especially at stop signs or reduced speed areas, and maybe Lucas knows this, definitely knows this better than I do, but all we really wanted to do is just look at the vehicle in front of it. But a lot of times there might be some other type of object that's downstream of it. So when we're looking at it, when we're looking at a vehicle, we can see clearly that there's a vehicle without any sort of stopping object in place, but we don't know what the vehicle in front of it is because it's telling us that the next thing is like a RSA or a stop sign or something along those lines. Or a ramp meter, or any sort of like stop control device, or other type of device that governs the the speed of the vehicle. So we had to do some additional filtering and say, if it's not a vehicle type in front of it, then we're just going to remove it out of the platoon. So that's something that we could probably enhance in the future, or ETV could, since they have it in Vissim. RSAs with high speed differential, and this is one but pass this back to Mike because he just gets so excited about the RSAs, and he also remembers that a lot better than I do. So go ahead and talk about your RSAs.
Fine. So this is a clip or a little snippet here. You don't have to play it yet from the, or you can play it now. When you have to go back and play it again because they have no idea what they're looking at now. So this is from our mountain pass example file. And we had really a low speed curve. And what was happening was, when we had, everything was uninterrupted flow. And so right now, you actually see it's a darker gray on the hairpin curve. We change it to an interrupted flow. And I'll kind of talk to you why about it. So the uninterrupted flow, what was happening is CAVs were entering it. And one might enter it, and once they cross the leading edge of the RSA, they set their desired speed decision to, say, 15 miles per hour. And a CAV vehicle that was behind it, say 300 feet, was saying, I'm setting my speed, and this wasn't something that we changed to, I'm setting my desired speed based on their current speed. We initially were saying if their desired speed is a certain value, that's what I want my desired speed to be. And then if they're gone for whatever reason, I'll reset my desired speed to some value that we've stored into another attribute. What was happening is we'd have a vehicle 300 feet back, the vehicle ahead of it would enter the RSA, and then once it fully entered the RSA, the trailing vehicle would now say, my lead target type is an RSA now, it's not a vehicle. I don't want to platoon with them anymore. I'm going to reset my desired speed now. Well, its last total speed was 15 miles per hour, and so it would just crawl up to that RSA. So we went ahead and said, well, what can we do to kind of get around this? And honestly, I was thinking of every way I could do it to not do this route and to not just make it an interrupted flow. And after racking my brain for hours on end, and I had a lot of ideas that I came up with that I tried, and none of them worked quite how I wanted them to work. And so this is the route we went with. And so what happens, and you'll kind of see it in the video clip, so that the dark blue vehicles are lead or single CAVs, the light blue vehicles are CAVs that have platooned into the platoon with the lead vehicle. And as the vehicles enter into that hairpin turn, they turn dark blue, they get out of the platoon, then once they get through the curve, they begin to join. They begin to join back up as a platoon again. So they're all entering. They're beginning to open up their space between them a bit because they're on freedom 74. They get through, and I'll point out one other thing we're doing here. And then once they get through there, they turn light blue again. They begin to want to form platoons once more. Again, you see some break in there because we've got platoon max sizes. One thing that I talked to John some about and others, and so just working on it, is when there's a speed change, vehicles would randomly make lane changes at points in time. And so what we ended up having to do is, if you look right downstream of that curve, we've got a no lane change for a few hundred feet or so. And basically we just did that so that the vehicles would make lane changes once they got out of the RSA. And so we did that wherever we had a speed increase. Any DSD, RSA, whatever, we put a no lane change for a distance there. So that was just one more thing that we had to add into our documentation of our framework and into our models just to make sure that we were capturing it all. Oh, and I mentioned we were initially using the desired speed decision of the vehicle ahead of it to set the desired speed of the vehicles behind. And what was happening was, we get into congestion, that vehicle ahead of it was being slowed way down, trailing vehicles were still saying, well, I still want to go 55 miles per hour, hey, I'm bailing out of the platoon. And we didn't want that. And so we said, we're going to base the speed based on their speed ahead of them. Well, even that didn't work all the time. What happened was the vehicle ahead of it would start slowing down, and it would force the trailing vehicles to compress just enough that they'd say, even though I'm trying every half simulation second, I'm trying to adjust my speed, I'm bailing out of the platoon. We ended up having to do a somewhat crude predictive speed check. So if the lead vehicle had an acceleration less than, well, we use 2.5 feet per second. If it was less than a certain value, the trailing vehicles would say, all right, I'm going to think about what their speed is going to be the next execution run of the script. So the next half second, what's their speed going to be? And I'm going to assign my speed based on their future speed. And when we did that, we ended up slowing them down a little bit faster. We kept the platoon's integrity intact, and they weren't bailing out of the lane anymore. And we said, well, that's 2.5 feet per second squared, maybe there's a better value. So we ended up making that an editable, user-defined attribute in that ini file that Kevin talked about too. So all these things that, how far apart platoons join, the max size, the deceleration rate of the lead vehicle, all these things are all user-defined attributes in this ini file. So if you want to play with things, you go in and you start adjusting things. Passing lanes. We had passing lanes on the two-lane state highway. So what was happening was trailing vehicles, one vehicle would go to pass, the vehicle behind it then would set its desired speed based on its current speed. What ended up happening was the vehicle would increase its speed like 20 miles per hour. Then the next vehicle would reset its original desired speed at like 20 miles per hour faster. So instead of being at 65, now it's 85. The vehicle behind it would increase its speed. Before we knew it, we had cars passing other cars at like 140 miles per hour. You know, so we had to go back and kind of reorder things in the platoon algorithm to make sure that didn't happen.
That was intentional, by the way. I meant to do that. So
He's just making sure I'm looking.
Or in Colorado, that does happen sometimes.
Not anymore, because you moved.
right, next.
Yes. So this is a clip, and this is an old clip. So this actually doesn't have our latest framework and the platoon algorithm in it. But I'll kind of show you a little bit on how it's working. So this was a divided rural. We had 50% adoption at this point. And I was just going to kind of show, we've got, in this clip, it's a platoon of 2, and we've got, I mentioned that we had a range of desired speeds for the vehicles. Posted speed, and then down to 5 miles below the posted speed. And so when we break these platoons up, what actually might happen is you might have a trailing CAV that really wants to go a little bit faster, but they're fine being in a platoon, they're happy, whatever. But once the vehicles begin to pass other vehicles, they go back to their original speeds. So, yeah, we're about done. So we'll kind of zoom in here, and we'll see. And there's some little word bubbles to kind of help us out along the way, remind me what else is happening. So we have a platoon of 2 cars in the outside lane here, and they're being passed. And what's going to happen is that blue car is going to want to pass that SUV in front of it. When he bails out, the pickup truck, he bails out of the platoon, and then he wants to pass, and then he gets out of the platoon, and then he sees the car in front of it and says, oh, I want to join with you, and then he begins the join process again. And then the vehicle gets out of it and says, okay, well, I don't need to be in the platoon anymore. Original desired speed was higher than the vehicle that was ahead of it. So he actually passes the CAV that he was following just before. This is how the logic works. I don't know that I necessarily like it, but it works in all these different facility types, and it works here. And so then the truck gets out of the lane, the car ends up coming over, and then joins into platoon once again. And that's it. Actually, this is actually a little bit longer time gap too. So the time gap is actually a little bit less in the framework that we have now. Some other results. So I'll tell you what, we developed the framework for the divided rural, and then we said this is working pretty well. Let's put it in the divided urban, and we did that. And we said, wow, there's a lot of stuff that doesn't work right. That's cool. And then I called Kevin, and he falls asleep, and then we do the whole thing over again. Then we got that working right. Then we get to the state highway with passing, and we figure out some more things. We get the mountain pass. We ended up making the framework applicable to all these. Okay, so it's something that we can apply to all these different facility types, and it works. The non-CAV operational behavior, and it's a lot of results vary for a number of reasons. The facility type, the operational behavior of the non-CAV. So if you've got a rural environment where you've got a lot more conservative drivers versus an urban environment, we get more aggressive drivers. I mean, you're going to see different gains, different capacity increases in these different environments. The adoption rate, obviously, if you've got 5% adoption, it's not going to do much. If you've got 85% adoption, a lot more opportunity. The platoon size, obviously another impact. I mentioned not wanting to get too crazy with the platoon size for reasons of mixed traffic. When you've got a lane that's not mixed traffic, there's more opportunity in those lanes. Just some somewhat obvious takeaways, I feel like, but I'll go through them anyway. So the capacity change is greater from the facilities where you have less access density. I think that's pretty obvious. But nonetheless, that's one of the results. The platoon on the mountain pass, I mean, you saw the platoons go through the hairpin turns and we were applying the framework. Platoons are disrupted. You get this accordion behavior, which I know Lucas talked about the accordion kind of behavior in the new release of Vissim. I don't think it is like what I'm talking about here, but you have this, platoons kind of expanding apart and then compressing back together again. The higher we got platoon adoption rate in the state highway model, the less passing there is. that makes sense, I think, because you've got speeds that all want to be about the same now. You don't have that great discrepancy between speeds anymore. But I had a little table there. I mean, that was just a quick check. So this is the divided rural. We had 25% adoption. Platoon size was at 5 cars, 3 trucks, and we saw about 7% increase in capacity. Not pretty nominal, I'd say. And that was based on trying to keep speeds about the same as a no adoption scenario, where you've got your density at like EF threshold. 75% adoption, again, we saw a better increase, 27% increase in capacity. Looked at the platoon size, double the platoon size, we saw even more increase in capacity. Again, that might not be what we want, we might not want something quite that long, but let's give it a shot. So we've used all of our time and then some. Well, I've used all of our time and then some.
Per usual.
Yeah.
You're right on time, Joe.
I'm right on time.
You're right on time.
So, I don't think we have anything else actually. No.
No. We can't take any questions, right? We went too far.
No, you've done it quite well.
Kevin can take all the questions that you have. We might even score one more touchdown.
So it seems
Joe.
like speed distributions for both ESDs and RSAs are a problem from a modeling aspect. Do you think some of those would be real life problems as AVs become adopted, and would there be necessary legislative kind of pushes to try and take those speed distributions and really set it at one speed on certain roadways, or take away some of that logic to make it easier to program in and have vehicles interact with each other?
I don't think it's as much of a challenge as maybe it appears here. I think that you're talking about like there's a couple things in there, I think. So you're talking about whether or not the speeds of the vehicles would be told to travel at some range of speed. Is that part of it, right? Or is that all of it?
The DSDs are a 15-mile-per-hour range for driver behavior.
Right.
But when you have a computer setting a speed, you can take those ranges and really condense them to something more similar. So your desired speed is 70 miles an hour and 70 miles an hour.
Right. I think that what we did is actually a simplified version of. I think what it's actually going to be is kind of more like our previous presentation here. I don't know if you're in here, but looking at more of this dynamic speed, and it's going to be based on a number of things. And like an urban setting, what I see is it's going to look at, and it's a mixture of what's the congestion look like. Let's adjust the speeds of CAVs to kind of speed harmonization of the facility. As maybe there's like a threshold based on what's a safe posted speed based on our design speed of the facility. Fine, 60 miles per hour. That's what we want to cap it at. But based on certain travel conditions, we're going to make it less. Yeah, the range in speed, I don't know. I could see it being minimized or nothing. For what we were doing, we really didn't have much of a choice. We kind of had to. But, yeah.
So I have a question about the table you show for the platoon size based on the roadway facility. If you go up. Yeah, here. So the platoon size for divided rural will be like 5 car and 3 trucks, right? But when I look at the divided urban, because divided urban has high AADT, you showed, but why the platoon size is lower in this?
Well, I think that was the last question probably, right?
Yes.
Yeah. Okay. When we are mixed traffic in an urban environment, lot of non-CAVs, lot of lane changing happening for access density. If we had long platoons, there's a lot fewer opportunities for those non-CAVs to make lane changes in between long platoons. I mean, honestly, if we would go in the urban model and try to put in longer platoon sizes, the non-CAVs, they didn't stand a chance. Trying to make lane changes and get cross platoons to exit at different locations. So that was one of the things that we really struggled with. And again, these are just samples. This is what we ended up using in the framework, but again, it is editable within the framework.
So we can say,
Gentlemen, I'm sorry. if we don't mind, could we hold some questions for a little after this?
Yeah, let's do
That's
that.
okay?
Yeah.
Don't want to move too far to the next person's time.
Yeah,
Guys,
thank
it's
you.
great. Thank you so
Hey,
much.
we scored a touchdown.